Just think about the chips inside your smartphone or the systems in your car, maybe the AI stuff that's everywhere now. These things are unbelievably complex. They represent, well, huge investments, money, time, sheer brain power. But there's this massive risk lurking, right? Finding a flaw after the chip is made. It's called a respin. Total nightmare. Can cost tens of millions, delay things by 6 months, maybe more. So the pressure to get it first time right is just immense. So how do they do it? How do tech companies make sure these super intricate designs actually work before they, physically exist? Well, today we're taking a deep dive into two really critical ways they do this before making the silicon: hardware emulation and FPGA-based prototyping. Our mission today, we're going to unpack how they work, look at their different setups, compare what they can do, and then check out the companies involved and what's coming next. So whether you're maybe an engineering student trying to get the basics or you're already in the field and curious about the latest stuff, this deep dive should have something for you.
That's absolutely right. And these aren't just, technical gadgets. Choosing between them or how to use them, it's a big strategic decision. It really affects whether a product succeeds and how fast it gets out there. Think of it like this. There's this huge gap in chip design. On one end, you have software simulation, which is super detailed but incredibly slow. And on the other end, the final chip, super fast, but you can barely see inside to figure out what's wrong if there's a bug. These tools, emulation and prototyping, they basically bridge that gap. They help you cross that chasm.
Okay, let's explore that chasm a bit more. We're talking about systems on chip, SoCs, and ASICs. These designs now have billions of gates, billions, driven by things like AI, cars, supercomputing, all the demanding stuff. And like we said, a respin is just catastrophic. The cost, the delays, it can sink a project. So designers use this idea, the verification continuum. At one end, like you said, software simulation, it gives you this amazing detailed view, right? Like X-ray vision for every signal, every register, super precise.
Exactly. But the trade-off is speed, or rather the lack of it. It's excruciatingly slow. Simulators run at what, maybe tens or hundreds of hertz? For a huge chip, that's like less than 1 clock cycle per second. So trying to boot an OS like Android or Linux or run actual software applications, that needs billions, trillions of cycles. It's just not practical. You'd literally be waiting forever.
And then the other end of the spectrum, the actual silicon, lightning fast, gigahertz speed, perfect. But almost zero visibility inside for debugging. If a bug pops up there, good luck finding it easily.
Right. It's notoriously hard. And that's where hardware-assisted verification, HAV, comes in.
Yeah.
It sits right in that gap. It uses real hardware to speed things up dramatically, lets you do way more testing before you commit to manufacturing.
Okay, so both emulation and prototyping fall under this HAV umbrella.
Right.
But they are the same thing. They're different tools for different jobs used at different times, right?
Exactly. They solve different problems in the design flow.
Okay, let's dive into the first one then. Hardware emulation. You're basically imitating the design, the DoD design under test, using special hardware, an emulator. The design code, usually RTL like Verilog, gets compiled into some special format for the emulator's own processors.
That's the idea. And its main job, emulation is really optimized to be the industry's best bug hunter.
Yeah.
It's a high-speed, high-capacity hardware verification and debug platform. What's unique is that it combines that deep simulator-like visibility with speeds that are, orders of magnitude faster than simulation. This combo lets you find those really deep, tricky bugs you'd just never hit in slow simulation.
Okay, that makes sense for finding the really tough hardware bugs. How do teams actually use these things day to day? What are the main ways?
Well, one common way is simulation acceleration. The design runs on the emulator, but the test code, the test bench, runs on a regular computer or workstation, speeds things up a lot. Then there's in-circuit emulation, ICE. This is pretty powerful. You actually connect the emulator to a real target system, like physically plug it into a prototype board or even a car's ECU.
Wow, okay.
Yeah, so you get real-world signals feeding the design, but you still have the emulator's debug power. And probably the biggest use case now is hardware-software co-verification, verifying the hardware and the software running on it at the same time. Essential for finding bugs where the two interact, which happens all the time.
Ah, those integration bugs.
Exactly. And finally, system-level power and performance analysis, PMP, identifying bottlenecks, checking power usage under realistic conditions, way before you have silicon.
So it sounds like emulation is really built to answer the question, did I build the design right? Does the hardware actually match the spec down to the details?
Precisely. It's all about functional correctness and deep visibility.
Okay, now contender number 2, FPGA-based prototyping. Here, you take the whole chip design and put it onto commercial FPGAs, field programmable gate arrays, which are like reprogrammable chips, right?
Sort of like a blank canvas for digital circuits, yeah.
So you're building a real working hardware model, a pre-silicon digital twin using these FPGAs.
Right. And its goal is different. It's about system validation and, crucially, early software development. While emulation focuses on finding hardware bugs with deep visibility, prototyping focuses on speed. It runs much, much faster, closer to the final silicon speed.
Yeah.
Its purpose is to check if the hardware, which is hopefully mostly correct by now, works properly in its intended system with the software.
That speed difference is huge, I bet. And that must enable things you just can't do on an emulator. What's the killer app for prototyping?
Oh, pre-silicon software development, hands down, no question. Because prototypes run fast, tens, maybe hundreds of megahertz software teams can actually boot full operating systems, Android, Linux, whatever. They can develop and debug complex applications way before the real chip is back from the factory. Trying that in an emulator would take, well, ages.
Right, that speed is key for software. What else?
Well, in-system validation is big too.
Yeah.
You can literally plug the FPGA board into the final system, stick it in the car's dashboard, connect it to the real peripherals, PCIe, USB, memory, validate it in its actual environment. It's also used for IP and subsystem validation, just getting a feel for how parts work. Because they're generally cheaper than emulators, you see them used a lot for regression testing, running lots of tests repeatedly, and even field trials or early customer demos. You can build more of them.
So prototyping seems geared towards answering a different question. Did I build the right design? Does the whole system, hardware and software together, do what it's supposed to do in the real world?
Exactly. And for that, you absolutely need the operational speed.
Okay, these different goals, verification versus validation, really show up in how they're built, their architecture. Why are emulators so much faster to get running to compile a design for?
Good question. There are basically three main architectures for emulators. First, processor-based, like Cadence's Palladium. They use custom processors. The RTL, the chip design code, gets compiled into instructions for these specific processors. The big win here, it completely avoids physical timing issues. That makes compilation super fast and predictable. A big design might be ready in just a few hours.
Okay, so fast compile means faster debug cycle.
Critical for hardware debug, yeah. Find a bug, fix it, recompile, run again the same day. Second type, custom FPGA-based, like Siemens Veloce. These use FPGAs, but FPGAs designed specifically for emulation, sometimes called emulator on chip or EOC, because they're purpose-built, mapping the design onto them, partitioning. Place and route is extremely fast, maybe minutes, very deterministic.
Ah, optimized FPGAs.
Right. And third, commercial FPGA-based, like Synopsys ZeBu. These use the biggest standard FPGAs you can buy off the shelf from companies like AMD. They offer huge capacity, but, well, they inherit all the complexity of standard FPGAs. Compilation takes much longer and is less predictable. You're fitting a square peg in a round hole sometimes.
Got it. Now, compare that to the prototyping systems. They all use those commercial, off-the-shelf FPGAs, right? Like Synopsys APS, Cadence Protium, Siemens ProFPGA.
Correct. They are fundamentally built from COT's FPGAs.
And they look different, too. More modular, lots of boards, daughter cards for real-world connections like PCIe, USB, Ethernet, memory.
Exactly. They need those physical interfaces to connect directly to target systems because they run fast enough to do so. But the biggest difference from a user perspective is what people call the compilation and bring up chasm. It's a night and day experience.
Okay, explain that. Emulation compile is fast hours, maybe?
Typically hours for a big design, yes. Highly automated. Find a bug, fix the RTL, recompile, run again. Often within the same workday. Super efficient for hardware debug.
And prototyping bring up.
That's the painful part. It's notoriously difficult, takes a lot of time, a lot of expert engineering effort. We're talking weeks, sometimes months, for a complex chip design. It's a major bottleneck.
Wow, weeks to month versus hours. What makes it so hard? Can you walk us through those steps again? Like, what does RTL modification feel like for an engineer?
Okay, yeah. First, RTL modification. Your chip design, the RTL, often uses structures perfect for a custom chip and ASIC. Things like complex clock gating schemes to save power or special memory types. These things are FPGA hostile. They just don't map well onto a standard FPGA's generic structure. So engineers have to manually, or using tools, change the design code to use FPGA-friendly equivalents.
Which sounds error-prone.
It can be, absolutely. Then design partitioning. Modern chips are too big for one FPGA, so you have to split the design across maybe 5, 10, 20 FPGAs. You have to carefully balance how much logic goes on each chip, and crucially, minimize the signals crossing between the FPGAs, because those connections are slow. It's like a giant, complex puzzle. Then each of those FPGAs needs to go through synthesis and place and route. Synthesis turns the code into logic gates. place en route, physically arranges those gates on the FPGA silicon and connects them. This is computationally intense. It takes hours, sometimes days, for each FPGA in the system.
And you might have dozens.
Easily.
Mm-hmm.
And finally, the step that often causes the most grief, timing closure. You've got this design spread across many FPGAs, all needing to talk to each other, and you need the whole thing to run reliably at a certain speed, say 50 megahertz. Getting all the signals to arrive at the right place at the right time across all those chips and interconnects, it's incredibly hard, highly iterative. You run P&R, it fails timing. You tweak something, maybe manually adjust placement, run P&R again for hours. That's the go home for the day debug loop. It's frustrating.
That paints a vivid picture. That chasm really comes from trying to shoehorn an ASIC design onto general-purpose FPGA hardware that wasn't specifically made for it, while emulators are purpose-built.
That's the core of it, yeah.
Okay, so given those bring-up differences, let's do a head-to-head on the key capabilities. How do they really stack up?
Right. Performance. Emulation runs in the kilohertz to maybe low single-digit megahertz range. Let's say 1 to 5 megahertz typically. Prototyping is way faster, tens to hundreds of megahertz, 10, 50, 100 megahertz, sometimes more. The impact. Booting an OS takes billions of cycles. On an emulator, hours. On a prototype, minutes. That's why prototyping is essential for software dev.
Huge difference. What about debug visibility?
That's where emulation wins big time. It offers comprehensive, simulator-like, full visibility. You can look at any signal, any register, any memory value, anytime. Deep trace buffers capture history. Perfect for finding the root cause of hardware bugs. Prototyping, much more limited. You typically have to decide beforehand which signals you want to probe. If you need to see something new, recompile. Which
Or
sticks.
day, maybe.
Right. So debug is much harder on a prototype.
Capacity. How big a design can they handle?
Both handle huge designs now. Emulation scales by connecting multiple cabinets together, tens of billions of gates. Prototyping scales by using more FPGAs, billions of gates too. But again, partitioning across many FPGAs bring up pain.
Okay. And connecting to the real world.
Yeah.
Interfaces.
That's a core strength for prototyping. Because it's fast, it can connect directly to standard interfaces, PCIe, USB, Ethernet, DDR memory, true in-system validation. Emulators are slower. To connect to those fast interfaces, they need special, often expensive hardware called speed bridges or rate adapters. Adds cost, adds complexity.
And finally, cost. The elephant in the room.
Yeah. Emulation has a very high upfront cost, millions of dollars for the hardware. And the total cost of ownership, TCO, can be 3 to 5 times that initial price when you factor in power, cooling, support staff. Prototyping hardware is much cheaper initially, thousands to maybe low 6 figures for a board, but the hidden cost is the massive engineering effort, the weeks or months of expert time spent on bring-up.
So it's not just a tech choice, it's a major strategic and financial one. High capital cost versus high operational cost and engineering time.
Exactly. It creates this crossover point people talk about. Early on, when the hardware design is buggy and changing rapidly, you need emulation's fast compile and deep debug. The pain of prototype bring-up is too high. Later, when the hardware is stable and you need to validate software at speed, the emulator's slowness becomes the bottleneck. You'll tolerate the prototype's limited debug to get that speed.
So they're complementary, used one after the other.
Very much so. Hardware verification teams lean on emulation. Software and system validation teams lean on prototyping.
Makes sense. Now, let's look at the companies making these tools and where things are heading. You mentioned the big 3 EDA vendors dominate this space.
Yeah, pretty much. Synopsys, Cadence, and Siemens ED. And they each have this dynamic duo strategy. Synopsys has ZeBu for emulation, HAPS for prototyping. They even have a platform, ZeBu EP, that can be configured for either. Cadence has Palladium for emulation, Protium for prototyping. They really push congruency using the same compiler front end. Makes moving from Palladium debug to Protium validation much faster, like maybe a day. A huge win.
A VIP pass, as they call it.
Something like that, yeah. And Siemens ED has Veloci for emulation, that's their custom chip 1, and ProPGA for prototyping. They also focus on congruent flows to ease that transition.
This integrated approach sounds efficient, but I guess it locks you into one vendor's ecosystem pretty tightly.
Oh, absolutely. Switching costs are very high once you're invested in one vendor's flow. And we shouldn't forget the FPGA makers themselves. AMD, now owning Xilinx, is crucial. Their big FPGAs like Vertex or Versal are the engines inside many of these systems, especially the COTS-based ones.
Okay, so what about the future? Where is this all going? You mentioned convergence.
Right, that's a big trend. The lines are blurring. We're seeing unified hardware platforms like that Synopsys example. One box that can do both jobs, configured via software. More flexibility, potentially better economics. We're seeing more congruent software flows, like Cadence emphasizes,
Yeah.
making it much easier and faster to take a design from the emulator environment to the prototype environment. Less friction?
Less rework.
Exactly. And also hybrid methodologies,
Mm.
mixing techniques like hybrid emulation, where you run parts of the design, maybe the processor cores, as faster software models on a connected computer, while the really complex custom logic runs on the emulator hardware. Frees up emulator capacity.
Mhm.
Or hybrid prototyping, mixing FPGAs with abstract software models, maybe System C models, for more flexible partitioning.
Interesting. What else is changing?
The cloud. Definitely the cloud. Emulation hardware is massively expensive, power-hungry. It used to be only the biggest companies could afford it.
Right. A huge barrier to entry.
But now, emulation as a service is taking off. Synopsys Cloud, Veloz Cloud. Companies can rent emulator time, lower upfront cost, pay for what you use, get burst capacity for crunch times. It really democratizes access. And prototyping is moving that way too, with cloud-based prototyping farms.
And what about AI? How is that fitting in?
AI is having a huge impact in two ways. First, AI chips themselves are a driver. Verifying these massive AI accelerators, especially for things like large language models, they need insane amounts of verification cycles, quadrillions maybe, pushing current tools to their absolute limits.
So AI demands are driving the need for better verification.
Yes. But second, AI is also an enabler. The EDA vendors are building AI and machine learning into their emulation and prototyping tools, using AI to help with things like smart design partitioning, optimize the place and route process for timing, even automating parts of debug.
Yeah.
Directly tackling that painful FPGA bring-up problem we talked about.
Using AI to tame the complexity AI itself creates.
Yeah.
So wrapping this up, what's the big takeaway for someone listening? It sounds like the conclusion is pretty clear. It's not about choosing either emulation or prototyping anymore. It's about using both.
Exactly. Emulation, AD, prototyping, they're complementary. You use them intelligently, strategically, at different stages, depending on what you need most, deep debug or high-speed validation, and considering your budget and team skills. And the ultimate goal, the big trajectory here, is creating this really detailed, persistent, pre-silicon digital twin.
A digital twin. So not just a temporary tool for pre-silicon checks, but a full replica of the system.
Yeah, a high-fidelity replica. You use it early for exploring architectures, then for hardware-software validation. But crucially, its life doesn't end when the first chip comes back. If a really tough bug shows up later in a customer system, you could potentially reproduce it on the digital twin, figure out the root cause, develop a fix or workaround, much faster than trying to debug on silicon in the field.
Okay, so it has value long after launch.
Definitely. You can use it to validate future software updates, firmware patches, ensuring they don't break anything or introduce new bugs into products already out there.
And I suppose it becomes the starting point for designing the next version of the chip, too.
Precisely. It's a foundational platform that spans the entire product lifecycle.
So this really reframes emulation and prototyping. They're not just insurance policies against mistakes, are they? They're fundamental pillars for how complex systems are developed, deployed, and maintained today.
Absolutely. This whole digital twin concept,
Yeah.
enabled by advanced emulation and prototyping, is how companies can innovate faster, ensure quality, and just manage the staggering complexity of modern silicon and software systems.
Well, for you, the listener, we really hope this deep dive gave you a much clearer picture of these incredibly sophisticated tools. Maybe next time you use your phone or see a new AI feature, you'll appreciate a bit more the immense engineering, especially the verification effort that goes into making sure that technology actually works. It's pretty amazing stuff. What part of this stands out most to you?